In this programme, we're going to talk about mapping the sky. But first of all, our news notes. Our first news note must be the launch of Mars Reconnaissance Orbiter, the latest spacecraft to go on its way to the Red Planet. And this is a very massive, very ambitious probe. Of course, it'll get there next year. It'll provide even better maps of the entire surface, analyse the surface materials, and also have a look to see whether they can see any traces of the grounded probes, particularly Beagle 2, which of course landed. Whether it came down intact, we don't know. Anyhow, Mars Reconnaissance Orbiter may find it. And Mars also is now nicely visible in constellation Aries, and you can see it as a bright red star. It comes to opposition at the end of October, and already even small telescopes will show surface details there and the white polar cap. There's also news from Saturn. I don't mean Saturn itself, I mean the tiny, icy moon Enceladus, ice-covered, and apparently there are ice volcanoes there, so it's an active world, and this is very unexpected. More about that next month. And what about the asteroids? Those tiny worlds, most of which keep to the area between the paths of Mars and Jupiter. One of these, 87 Sylvia, has now been found to have two tiny satellites, now called Romulus and Remus. This is the first triple asteroid. As you know, we've been through the annual Perseid meteor shower. This happens every August. Between late July and mid-August, we see a great number of these meteors. And this year, it was a pretty good shower, and the moon was out of the way. And we had a meteor watch at my observatory.
Brightest one on a wide field.
Oh, a nice one, diagonally across there.
Again, very short.
Well, here we are, clustered around the observatory dome in my garden at Sept, and we started our Perseid watch, the Perseids of 2005. Well, it's not perfect. There is some cloud around, there are also some clear spells, and we've seen several meteors already, of which one was bright. But it's only just after 11 o'clock summertime, and the rest ones just come after midnight. So we're going to wait here and hope for clear skies and some really good displays of cosmic fireworks.
Oh, wow!
God, he missed it.
Beauty! Right for the radiant. Oh, now there's an interesting sporadic.
At least, John, if we set out here for a few hours with a reasonable sky, we are bound to see a few Perseids. They're the most reliable shower of the year.
They are very reliable, and of course the other advantage of the Perseids, of course, as we're witnessing now, is that the weather is extremely mild. Most of us are sitting out here with a very little in the way of heavy clothing on.
And no moon tonight.
No moon. No, the moon's gone down, which is another advantage, of course, in that we haven't got any scattered moonlight to destroy the show. The Perseid radiant at the moment is still quite low, just below the left-hand stars of Cassiopeia in the top of Perseus.
You can see Cassiopeia well from here, of course.
You can. So, I mean, as the hours go by and the radiant gets higher, the rates will pick up. Oh, wow!
That's got to be close to where I'm looking.
Right through Cepheus. Oh, wow!
Where was that?
That was just above Polaris. Nice train on it. Little sporadic there in Cepheus.
Oh, I saw that, small one.
Yeah.
How bright was that?
One thing I've noticed, John, we have long quiet periods and then 3 or 4 meteors at once.
Yes, this is actually quite common when observing meteor showers. You get a period where you might get 2 or 3 in a minute, and then there's a lull of several minutes where you don't see anything. And this has led many people to say, well, the meteors are not occurring at random, they're occurring in clusters. But I did an analysis of this some time ago and measured the times accurately of every meteor seen. And when you plot them out, they really are occurring at random.
Illuminates the sky. Oh, that was a beauty!
I think it's fair to say we can count this meteor watch as a success. No fireball, nothing unusual, but we have seen quite a lot of Perseids, and it has been great fun.
Oh, there's a nice one.
You might like to see some of the pictures. Here's one by Mark Parrish, a lovely Perseid, and this one by Pete Lawrence. It was a good display. Of course, you can see meteors at any time of the year, although August is always the best month. And now, for the eclipse of the sun on October the 3rd. It's partial from here, more than 60% of the sun eclipsed. It'll be annular from Spain, and that's where Chris Leonard's going to be with our Sky at Night team. But from here, we may have a good view, but please let me give you the usual warning. The sun is dangerous. Don't stare at it, even with sunglasses, and above all, don't look straight at the sun through any telescope or pair of binoculars. If so, you'll blind yourself. The best thing to do, turn the telescope sunward and project the image onto a screen, but don't look direct, and things like sunglasses, smoke glass, they're no good. So please be careful. Interesting eclipse there, so let's hope for clear skies. Our main theme tonight is mapping the sky, and two important surveys are now in progress. Chris Flintoff went to Palomar Observatory to see the great 200-inch telescope there and to see the results of some of the earlier surveys.
South of Los Angeles on Palomar Mountain is the home of the 200-inch Hale telescope. When it was built in the 1930s, it was far ahead of its time and remained the largest telescope anywhere until 1993. It's difficult to remember now how far ahead of its time the 200-inch in its iconic massive dome actually was. The first two attempts to cast such a massive mirror were complete failures, eating up over $1 million in the process. Professor Richard Ellis is the director of Caltech Optical Observatories, who own and run Palomar.
Well, this is the 18-inch, which is the very famous one that Zwicky used to look at supernovae and classify them. Of course, everybody knows the famous 200-inch, which is behind us here, but there are many other telescopes here, including the famous 48-inch, which did, of course, the National Geographic Palomar Sky Survey. We have a 60-inch telescope here that is now being modernized and looking for gamma-ray bursts. And of course we're upgrading the 200-inch with new instrumentation all the time. So this is a very famous historic observatory, but it's a fully functioning modern observatory with many scientific discoveries coming out all the time.
When the 200-inch was built, it was way ahead of its time.
It was a very innovative design. The mirror, the Pyrex mirror, was a breakthrough in the manufacturing of large optics. The engineering was a great challenge, of course, during the Great Depression in the 1930s. Finally, the war intervened and it was fully commissioned in 1948. So it's 55 years of full operations now, and the instruments on it now you wouldn't have recognized in 1948. We have a panoramic infrared camera, a modern detector inside it. We have a laser that's being used for adaptive optics, very high angular resolution images of distant objects, and our other telescopes have been automated and modernized too. So Palomar, I think, is a very good example of how an observatory can last for decades, evolving its instruments according to the changing needs of modern astronomy.
In order to use adaptive optics to remove the effects of the Earth's atmosphere, astronomers need to know what the atmosphere is doing. If a bright star is nearby, then we can watch it twinkle. But not all objects have a convenient star close by. So here, they're developing a system which provides guide stars on demand.
We need to have a bright star available to us, and so we take the matter into our own hands and we project a laser beacon into the sky to create a guide star that allows us to measure the Earth's atmosphere on the timescales that we need.
And it's not quite as simple as looking at the beam of the laser. It's more clever than that.
Yes, in fact, we take advantage of a unique feature of the Earth in that there is a thin layer of sodium atoms in the mesosphere. The mesospheric sodium resides about 90 kilometers in altitude, so it's really far above what we would call the atmosphere. It's at the edge of space. And it provides a sort of a projection screen onto which we can shine a finely tuned laser and look at the backscatter return from that mesosphere.
How far has your development of the system got?
Well, here at Palomar, we've projected the laser onto the sky and measured the return from the sodium layer. We are working on the next few days of getting that incorporated with the existing adaptive optics system.
So when will it be available for science?
Well, it really depends how our engineering goes. We predict it's probably another 2 or 3 months until we begin to do science, and then as rapidly as we can, we'll turn that over to the faculty and to their students.
Whoa, it's getting brighter.
Wow. Over the years, Palomar has made many amazing discoveries. We were here for the Deep Impact mission just a few months ago. Discoveries include the first unambiguous image of a brown dwarf, Comet Schumacher-Levy 9 prior to its famous impact with Jupiter, and, in the 1960s, the first quasar. Patrick was last here in 1981, when he talked about why this telescope is so special.
There's one point that I always find interesting.
The mirror is coated with a thin layer of aluminium, and by thin, I mean thin, the tiniest fraction of a millimetre.
It's this aluminium film which collects the light from the object you're observing, and so the whole telescope, with its 500-ton mass and its 1,000-ton dome, exists merely to move this flimsy aluminium layer around.
For a long time, the observer stationed himself in a cage actually inside the telescope tube. The telescope was designed to study objects a very long way away from us. Although in the very early days, some lunar and planetary pictures were taken, and some of those, such as the picture of the crater Copernicus on the Moon and the red spot on Jupiter, have been reproduced time and time again. But that wasn't the purpose of the 200-inch. Its role lay among the stars and galaxies.
To select distant and faint galaxies for the 200-inch to observe, astronomers needed a map which covered the sky in unprecedented detail. The famous Palomar sky survey was commissioned to cover the entire sky with images including the faintest objects possible.
It was done in the 50s largely, the original survey. It was done with the 48-inch Schmidt telescope, which is as old, in fact, as the 200-inch telescope. Remarkable planning that we devised a wide-field survey telescope alongside the famous 200-inch, which you see behind me here. Now, that sky survey was a photographic survey, and it was important in understanding the counts of galaxies, their sky distribution and their clustering, and it is the forerunner of many of the more detailed surveys that have been done with many telescopes around the world since.
And survey astronomy now, looking at large areas of the sky and hundreds or thousands of objects, is a really important part of astronomy today.
It's a very important part of astronomy, not only in finding objects for further detailed study, and that was the original synergy that was so successful between the Palomar Schmidt and the 200-inch, but also in understanding the nature of the universe, for example, its constituents. So, for example, when we look at the sky distribution of galaxies, we think that their clustering is telling us something about the presence of dark matter. And how that clustering changes with time is telling us about the nature of the interaction between dark matter and other mysterious constituents of the universe.
Okay, so what telescope is this?
So this is the 48-inch Schmidt, now Samuel Ocean telescope, and it's been refurbished to include these big CCDs. And
it's instantly recognizable.
The Hubble picture, of course.
Oh, just here, of course.
Yeah, right here.
Yeah.
This is one of the sky survey plates that was taken with the Samuel Ocean 48-inch Schmidt. It's truly impressive because it covers an area 6 degrees on a side. So that's, about 1,200 of them were needed to cover the northern sky. And this one has got the Andromeda spiral galaxy on. It's a beautiful plate,
yeah,
as you can see.
The detail is amazing, not just in Andromeda, but in the rest of the plate as well.
Yes, so this was dominant technology from 1950 right through till the late 1990s. So
and that's how long the survey took?
Absolutely. We did a sky survey in the 50s, then we went back and we did a second-generation survey for moving objects, and of course we did it in many filters.
And that work finally came to an end in 1999, and the telescope has now been refitted for the modern era.
Completely. So what you see now is a telescope that's been completely refurbished. It has 112 CCD cameras in, and it's doing drift scans of the sky to look for supernovae and moving objects in the outer solar system.
The Palomar survey remained as the best guide to the sky for astronomers for 40 years and is still used today. The beautiful plates reveal not just individual objects, but the universe as a whole.
The Palomar Sky Survey was a great step forward, but now we're having new surveys with modern telescopes and the most modern electronic equipment. I'm delighted now to introduce two people who are very deeply concerned with this, Professor Carlos Fink and Professor Bob Nichols. Welcome to the Sky at Night. Bob, what does it feel like to be a sky mapper?
It's wonderful. I say to most people it's the most noble profession you can do, and that is to just go out there and map the universe and see what's out there and write it down on a computer disk and understand it.
Do you feel that too?
Oh, absolutely. Mapping is as old as civilization. And just as we mapped the Earth and we mapped the continents, now we're beginning to map our cosmic neighborhood.
Goes back to Ptolemy. Now, what about the sky survey you're particularly concerned with?
I'm involved in something called the SLOAN Digital Sky Survey, which is probably one of the most ambitious cosmology and astronomical projects we've ever done. What's unique about it is that we do both a digital imaging survey of the sky and then follow it up with a spectroscopic survey of the sky. So it's the marriage of those two things.
What about your particular survey?
Well, our survey is a primarily Anglo-Australian collaboration. It's called the 2DF survey. 2DF stands for the name of the instrument in the Anglo-Australian telescope, the 2-degree field instrument. The telescope was adapted to have a large field of view so that we could map and survey the universe. Unlike the SLOAN, which is a more ambitious effort, the 2DF survey was really targeted at some very pressing and important cosmological questions. The questions we tried to answer were related to the large-scale structure of the universe and to how the universe has been evolving to produce the galaxies that we see today. But the basic technology that underpins the two surveys is the ability that we now have to take many spectra at once using fiber optics that allows, in the case of 2DF, to measure 400 galaxy or quasar spectra at once. And that was a technological breakthrough, the ability to use fiber optics in order to multiplex and take observations of a collection of galaxies or quasars all at once.
What are the most important results so far?
Well, there's quite a few of them. We had a two-day meeting to discuss the answer to this question, but I think in my mind, stepping back, I think what the 2DF survey has achieved has been really to bring cosmology into a new plane where theories can be tested against observations at a level of rigor and accuracy that was unthinkable 10 years ago.
The SLOAN survey is now going on, isn't it?
It is. We just got funded for 3 more years, which is fantastic. So it'll carry on until, thank you, it will carry on until 2008, the middle of 2008. And it has actually 3 things to it. So it's not just exactly the same as what's gone. So the 2 new things the SLOAN will do is it's going to do a map of our galaxy. It's going to do hundreds of thousands of stars in our galaxy and study the motions of stars in our galaxy. So that'll be a fantastic resource to understand where our galaxy came from. And then the second one is to look for these very distant supernovae that go bang in the night, and we use them as cosmological probes to find out the distance scale in the universe. So there are those 2 new aspects to it.
What unexpected discoveries have you made with these surveys?
Well, we discovered what I would call the birthmark of the universe. And what that was a signature that had previously been detected in the microwave background radiation, the heat left over from the Big Bang. There is a characteristic feature in that radiation that, to our enormous surprise, has survived the passage of time and can still be detected in the galaxy distribution today. It's a sort of birthmark of the early universe.
That was, for me, one of the major things we discovered in the SLOAN.
That was unexpected, completely unexpected.
Of course, we see galaxies of all kinds.
There are lots of galaxies out there, but they tend to be sort of 2 types. There are red and dead, sort of elliptical type galaxies, which we think were formed very early on in the universe. And then there are things like our own galaxy, which are spinning disks full of blue young stars and seem to be evolving and active today. So it is a conundrum that we have these 2 types of galaxy. I mean, I would use it, we have boys and girls, right? And you know, why do we have two types?
What I think the theory may be telling us is that these 2 types are not set in stone, but that galaxies can evolve from one type to another, then that in fact they can come and go from being elliptical to being spiral to being elliptical again. That is what at least our computer simulations are telling us, that the type of a galaxy is a fluid concept, and that galaxies can go from being of one type to being another type.
Can we say a bit more about quasars, formerly thought to be faint stars and now known to be immensely powerful and immensely remote, I mean, millions upon millions of light years?
We think they're supermassive black holes that are accreting matter at about something called the Eddington limit. So that means shoving matter onto this black hole as quick as you can while the pressure of the light coming out is trying to stop that matter coming on. So they're sort of accreting at the maximum rate they possibly can. So that's where the radiation that you see is coming from.
One of the most exciting developments, to some extent triggered really by these 2 surveys, is the realization that quasars seem to be playing a key role in the formation of every single galaxy, including our own Milky Way. We're now beginning to think that even the number of galaxies that we see in the universe have to do with processes involving quasars, and that every single galaxy, including the Milky Way, went through a quasar phase where a black hole in the center accreted matter and produced these amazing outputs of light. So I think quasars may hold the clue to understanding the origin of galaxies.
Well, your survey is still going on. Yours isn't. So what are you going to do next?
Well, we are trying to still interpret the data from our survey and from the SLOAN survey as well. And one of the things that we have been developing very actively, and I think it underpinned a lot of the science that came out of the survey, was the development of computer simulations, very sophisticated and realistic computer simulations that allow us to recreate the evolution of the universe and allows then to see whether what we observe is actually what we expect to observe on the basis of theoretical ideas. What the simulations do is that they allow us to run the movie, whereas observations gives us snapshots in time. Right. The simulations can fill in the gaps. And so as the simulations have become increasingly realistic, we've been able to model in greater and greater detail the evolution of galaxies. What we're able to do now very well with the simulations, and I think pretty much to the degree of accuracy that's required, is model the evolution of the dark matter.
What's the next survey going to be, and when will it start?
I think it's a very intriguing time right now. There's a lot of planning going on right now. There's a lot of people talking about the next generation of surveys. I think over the next year or so that will come to fruition, and we'll know about which surveys are going to go forward in the next 5 years. There's obviously new imaging surveys. People want to go deeper than, say, the SLOAN or 2DF. There are new redshift surveys, so people want to sort of study millions of galaxies at high redshift now instead of just looking at our local universe. So I think survey astronomy actually has a very good future. It's just right now we don't exactly know the direction.
So we're in a very strange situation. We know a lot about our universe when it was a mere 380,000 years old, which is when the heat left over from the Big Bang was produced, when it was the microwave background radiation was generated. And this tells us directly about conditions that prevailed in the universe at this very early epoch, 380,000 years after the Big Bang, the human equivalent of one day. We know a lot about the universe then. We know a lot about the universe today, but we know rather little about what happened in between. The SLOAN survey has given us glimpses of what happened a billion years after the Big Bang, and other surveys have told us a few little things about what was going on 2-3 billion years after the Big Bang. So I think the interest now really is in trying to do surveys of this magnitude, but bridging the gap between the early universe and today.
Well, yes, but have you any possibility of looking back to the Big Bang itself, do you think?
That will probably be done not with the sort of surveys we do, but with there's this fantastic opportunity now to use things like gravitational waves. So people are starting to think about building satellite interferometers where they have satellites coordinating with each other to incredibly high precision, and then using that to detect gravitational waves potentially from the beginning of the universe. So I think it'll be using that sort of radiation, not optical radiation, to see the first instant in the universe.
We've come so far since I began the Sky at Night program, but now the Palomar 200-inch telescope was in a class of its own. And since then, so much has happened. Well, I wonder, what's the most exciting thing you expect in the next 50 years?
Well, first of all, I really would like to know the answer to the two questions which I think are the most pressing, not just in astronomy or in cosmology, yes, or indeed in physics, perhaps in the whole of science, and that is, what really is the dark matter and the dark energy that we know dominate the content of our universe. We know they account for 95% of what's out there. We know these two elements or these two components exist. We see their effects, but we don't know what they are. So to me, answering the two questions, what is the dark matter and what is the dark energy, must be the overriding goal of physics and cosmology. Hopefully not for 50 years. I hope we'll find the answer, at least to the dark matter question before then, but certainly for the next few decades.
Well, yeah, we talk about dark matter and dark energy. What's the difference?
Well, that's a good question. Well, the dark matter, we think we have a physical explanation for it is, and Carlos knows this better than I do. We think we have a theory for it and how it sort of clusters and how it operates. So it sort of Carlos can run a simulation and tell you what the dark matter should look like. We have nothing like that for dark energy. We're almost clueless, I would say, about what the dark energy could be. So at some level, they're both dark and they're both unknown to us, but I think we can make some physical intuition about what the dark matter may be. We have no physical intuition of what the dark energy is.
But let me just say one thing, see if Bob agrees and you, Patrick, about this. I think in the case of dark matter, the name is well deserved. Because we know it's matter and it's dark.
Exactly.
In the case of dark energy, I think the reason for using the word dark in this context is just because we know nothing about it. It's dark to our understanding, but it's not dark in the same sense that the dark matter is dark.
Yeah, quite. How are you sure it's there?
Well, there are now tremendous amount of information, but both out of the 2DF and SLOAN, out of supernova observations, the CMB. There's such a weight of observation, there's such a weight of information and evidence that we're missing some component in our cosmological model, and that component, whether you call it a dark energy or whether you call it a modification of gravity, there's something intrinsically missing in our present cosmological model. I think either Carlos said it or other people have said it, that we, believe it or not, we can predict what the model should look like extremely well now with our model. We just have no idea what components are in the model. We have little physical intuition of what's in the model.
Yeah, in a computer, we can make universes that work, but they do require dark matter and dark energy. Even though we don't know what they are, we can still make universes that work. I can probably make a car that works, that runs, even if I don't understand necessarily the thermodynamics of combustion, for example.
You know, if we could come back in 50 years and have a discussion like this, looking back at what we've said in the last few minutes, it will probably be completely out of date and much of it may be wrong. Is that correct?
I would, if I can just jump in there, I would say that whatever we predict won't be the interesting thing that we talk about in 50 years. And I think that's something that's come out of both these two surveys, the SLOAN and 2DF. We've discovered things that we never even imagined at the beginning. So these predictions can be very dangerous because they may not be interested in 50 years.
Well, I would be slightly more upbeat. I think that it's true. We don't know what the dark matter is. We don't know what the dark energy is. But when these questions are unraveled, whatever the dark matter and dark energy turn out to be, they're going to look a lot like what we think they are now. Because now we have the ability to make universes that work. So whatever is there, it has to, if it's not dark matter, it has to do the same role of dark matter. If it's not dark energy, it has to behave like dark energy. So I think that the discoveries that have been made in the last 2 decades will stand the test of time and will still be valid and exciting, although perhaps subsumed within a much bigger picture in 50 or 100 years from now.
The surveys you've been carrying out have told us a great deal. There's much more to be learnt, but these will form a basis for all future research. Carlos, Bob, thank you very much.
Thank you.
Thank you, Patrick.
When I come back next month, I'll be talking about the forthcoming meeting of the Division of Planetary Sciences, which is being held in Cambridge. Until then, good night.